Hello, I'm Charlie Thompson, and this is the second video for the first chapter in physical geography. Let's pick up with Module 3, talking about systems, Earth systems. So systems theory, a system is a set of components linked by energy flows. So it's physical stuff linked by flows of energy and linked by flows of other physical stuff. Systems we describe as open. They can be open to energy or open to matter or closed. Closed systems almost are non-existent in nature. Just about all the systems in nature are open. Earth is kind of a tough example to use. I would say Earth is open in terms of energy, certainly. Energy comes in from the sun, it warms up Earth, it evaporates water, it makes wind and weather, and then that heat goes back out to space. In terms of matter, Earth gets a couple tons of dust every day from space, so we get tons of space dust, but we don't get new usable good stuff. We don't get new computers plopping in from space. So I would say Earth is open in terms of energy, and Earth is probably closed in terms of matter. It's not very important, because Earth is still going to be there regardless of whether we think it's open or closed to matter. Every now and then, something like 65 million years ago, an object about 6 miles across about 65 million years ago, an object about 6 miles across impacted off of Mexico with enough energy to ignite global forest fires and make the dinosaurs go extinct. So every now and then we get physical stuff from space. But when we're looking at systems, another important aspect of systems is we define what the limits of that system are. So you, the person studying it, you, the researcher, are the one that defines the system. So they're artificial, right? That division doesn't really exist. Like a system, I could say, I'm going to study the Big Basin Forest. And so that's going to be my system. That way I don't have to study everything in the universe at the same time. I can just focus on this system, which is going to be open to matter and energy. Air comes in, water comes in, air and water go out, sunlight comes in, light energy comes in, heat energy goes out. So a forest, it's completely open to energy, completely open to matter. And most systems, in fact, almost all systems in nature are open to both energy and matter. So again, looking at a forest, the inputs, sunlight, air, water. The plants make sugar and oxygen from water and light. The outputs are oxygen and sugar and trees. And then there's also often a human environment connection with a system. How does that system influence people? How do people influence the system? As the system is working, the behavior of the system can influence the system, and that's called feedback. Feedback, I think, is poorly understood. Most people are confused about feedback. You can have a feedback loop where the output of a system affects the behavior of that system and either makes that system do more or do less. So if the output of a system makes that system do less, that's negative feedback. Negative feedback reduces the behavior of the system. Negative feedback stabilizes systems. So the way we are most used to talking about feedback, you can have positive feedback or negative feedback, and positive feedback is good and negative feedback is bad. That's not the way feedback works in nature. The idea of it being good or bad, that's just a human idea. So negative feedback tends to stabilize the system. Positive feedback increases the behavior of the system and destabilizes the system. So in nature, negative feedbacks stabilize system. Our bodies have a whole lot of negative feedback loops. For example, you feel thirsty, and the response of your feeling thirsty is you think, oh, maybe I should drink something. When you drink something, changes occur in your body and you no longer feel thirsty. That's a negative feedback. Same thing with being hungry. I'm hungry. I eat food. I'm no longer hungry. That's a negative feedback. Positive feedback would be a wildfire, would be a good example of positive feedback, that as the fire grows bigger, it gets hotter, so it burns more. As it burns more, it gets bigger, and it gets hotter, so it burns more. And you can see that process is just going to continue until something changes, until it runs out of fuel or something else about that system changes. But forest fire, and out of control, rapidly spreading forest fire, would be an example of a positive feedback loop. That's also a good example of why positive feedback isn't necessarily a good thing. Oh, this is a mechanical governor, a mechanical feedback apparatus. So the way this works, these were used in old antique engines, and this shaft is connected to the engine. There's a pulley, and so as the engine goes faster, this spins around faster. As it spins around, the balls fly up, which moves this lever, which reduces the gas going to the engine. So the engine goes more slowly, so it spins more slowly, so the balls come back down, which moves the lever, which opens it up. So think of it as a cruise control. It's like a really primitive cruise control, and this is a negative feedback loop. When the engine goes too fast, it moves the balls, which move the lever, which shuts down the flow of fuel to the engine, so it goes more slowly. If it goes too slowly, it opens back up and it gets more gas, so it goes faster until it goes too fast, and then it gets shut down. So an example of a mechanical feedback loop. And then this would be an example of negative feedback because it's stabilizing the system. It's keeping the engine operating at a certain level, not too fast, not too slow. So here's another feedback loop. This would be the ice albedo feedback loop. So ice reflects a lot of energy. So 95% of the sunlight coming into ice bounces back out into space. So when sun shines on ice, the light gets bounced back into space. But as temperatures rise, the ice melts, which exposes dark water, which absorbs heat. Because now it's less reflective, the ocean absorbs heat, which increases the temperature, which melts the ice. So there's more water exposed, which absorbs heat, which makes temperatures rise, which melts the ice, which exposes more dark ocean, which then absorbs heat. So this is a positive feedback loop. In fact, most of the feedback loops involved with climate change are positive feedback loops. As temperatures rise, more water vapor evaporates, which goes into the atmosphere, which absorbs heat, which makes the atmosphere warmer, which evaporates more water, which goes into the atmosphere, which absorbs heat, which makes the atmosphere warmer. So those are just two positive feedback loops. Both of them are bad. So let's talk about system equilibrium. System equilibrium is the idea that a system would have a given level of behavior. You could have different types of equilibrium. The behavior could be changing, in which case it would be a dynamic equilibrium. You could have steady state equilibrium, where the system remains more or less the same over long periods of time. Probably very rare in nature. There are thresholds in systems, a tipping point where a system shifts to another state. A good example of a threshold with a tipping point would be a light switch. So as you flip on a light switch, if the room was dark and you slowly flipped the light switch, nothing would happen. You could move it a little bit, nothing would happen. You could move it a little bit, nothing would happen. And then when you move it that last little bit, the switch is going to flip on its own and the lights are going to come on. And that's an example of a nonlinear response because the response wasn't linearly related to the input. So the input was small and nothing happened, small and nothing happened, small and nothing happened, small, and then suddenly something happens. So a lot of natural systems exhibit nonlinear responses. The Amazon is a good example of a system in nature that is potentially going to demonstrate a nonlinear response. So as climate is changing, as the planet's getting warmer, the Amazon is beginning to dry. And the water in the Amazon is very local. So the rain that falls in the Amazon is going to get picked up by the plants and it's going to evaporate. It's going to make clouds and then it's going to rain tomorrow in the Amazon. It's going to get picked up by plants. It's going to evaporate. It's going to make clouds. It's going to rain the day after. So what happens as the Amazon dries is small changes, small changes, small changes. But once it dries, that last little bit, there is very real danger that the Amazon is going to flip from being a tropical rainforest to just being a desert because there won't be enough water vapor in the system to keep the system going. So there's going to be a sudden shift. That's an example of a non-linear response where you lose a little bit of water vapor, nothing happens. Lose a little bit of water vapor, nothing happens. Lose that last little bit of water vapor, and the system changes rapidly. Some examples of the systems that we'll be talking about in this textbook. There's the atmosphere, the gassy part of Earth. There's the lithosphere, that's the rocky part of Earth. The biosphere is the living part of Earth, and the hydrosphere is the watery part of Earth. So there's three abiotic. A means not, biotic, living. So not living. The watery part of Earth, not living. The gassy part of Earth, not living. The rocky part of Earth, not living. The biosphere, which would be the circle of life. The biosphere would be the living components on Earth. So 3 of the 4 systems are going to be abiotic. The last, the biosphere, is going to be a biotic system. Ooh, that's a good place to keep going. Locations and time, very, 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 very important for geographers. Geographers are concerned with where things are. Well, that's part of location, but location is also the ability to go back to a place. So let's talk about Earth's dimensions, some numbers you're going to need to memorize, definitions. Geoid. Earth is a geoid. The technical name for the shape of Earth is a geoid. A geoid is a Earth-shaped object. It's totally cheesy. If you're a scientist, you get to make up cheesy definitions. So the definition of a geoid is Earth-shaped. What is the shape of Earth? Oh, Earth is a geoid. What does geoid mean? It means Earth-shaped. It's a sphere. Some numbers you need to know. Equatorial circumference of Earth, 40,075 kilometers. You totally need to memorize that. Polar circumference, 40,008. So you can see if you walked around the equator, you'd have to walk 40,075 kilometers. If you're able to walk from the North Pole to the equator to the South Pole back up to the North Pole, that would only be 40,008 kilometers. Earth is bulgy. It has a geoidal bulge. It has love handles. It is middle-aged. So Earth used to be molten. When it was spinning, it got bulgy across the equator. If you notice, if you were to measure the distance from one side of Earth to the other, it'd be 7,926 miles. Going from across the equator, if you went from the North Pole to the South Pole, it's only 7,900 miles, a savings of 26 miles if you were going to walk through the Earth one way or another. I would walk from the North Pole to the South Pole. You'd save 26 miles. The metric system. The United States is one of 3 countries. The United States, Liberia, and Myanmar are the only 3 countries on the planet that don't use the metric system. Everybody else uses the metric system. So for this semester, we'll use both the metric system and the system that we use. As of 247 BC, that marks the first time that humans were able to calculate the circumference of Earth accurately. Eratosthenes, the librarian in Alexandria, was able to calculate the circumference of Earth within a couple percentage points using shadows. So everybody knew Earth was a sphere. Nobody thought Earth was flat. That was a lie that was started by a book that was actually published only in 1830 in London that said the big deal with Christopher Columbus is everybody thought the world was flat. They just made that up, and other books just copied that and printed it, and so now people think the big deal with Columbus was the Earth. People before that thought the Earth was flat. Well, they didn't. They knew Earth was round. Eratosthenes in 247 realized on the summer solstice, when the sun is as high as it's going to get over the northern horizon for the year, that there was no shadow. The sun was hitting the surface at a 90-degree angle. And he thought, that's weird. When I'm at home, slightly to the north, on the same day of the year, the summer solstice, there is a shadow. The shadow has an angle. And he thought, wait a minute. So if the sun's shining here, the sun's hitting at a 90-degree angle, and here it's not hitting at a 90-degree angle. Well, the distance, the angle between these two places through the center of the Earth, the angle is going to be, the angular distance between these two places is going to be equal to the difference in the angle of the shadows. So I just got to back up and go over this again because I'm just so impressed. 247, Eratosthenes knew when he was at home on the summer solstice that the sun cast a shadow. He's in Syene. He realizes that there's no shadow, and he intuitively knows that the distance between them, the angular distance between them, is equal to the difference in the angles of the shadows. And that once he has that, he can calculate the circumference of Earth. And he did that like this. No angle. There was a 7.2 degree angle. So the difference between these two places was 7.2 degrees. In this case, it's 7.2 degrees of latitude because it was a north-south difference. So he knows that from Alexandria to Syene is 7.2 degrees of latitude. He also knows that 7.2 degrees is 1/50th of Earth's circumference. So the distance from here to here is 1/50th of the distance all around the Earth. So all he has to do, he can't measure the distance around Earth going that way, but he totally can measure the distance from here to here. And then multiply that by 50, and you'll get the whole circumference of Earth. And that's exactly what he did. So in 247 BCE, Eratosthenes was able to calculate the circumference of Earth within a couple percentage points. Amazing, phenomenal work. Compass directions, north, south, west, east. We're on the west coast. New York is on the east coast. The North Pole is on the other side of Canada from us. On the other side of Mexico and South America is the South Pole. In between are intermediate. In between north and west is northwest. In between north and east is northeast. In between south and east is southeast. In between south and west is southwest. So the reference grid, latitude and longitude. Latitude is the angular distance north or south of the equator. Lines of latitude are called parallels. These are some locations, some latitudinal zones, because latitude is one of the most important, if not the most important concept we'll talk about this semester. Not just the idea of latitude, but where things are with regards to their latitude is going to be one of, if not the most important things we'll talk about. So there are 5 different zones you're going to need to memorize. There's the equatorial region. The equatorial region largely lacks seasons. Every day there is about 12 hours long. Temperature's about the same. It's probably going to rain in the afternoon for a bit. And that's going to be the way every day is like in the equator. So going from the equator, where every day is 12 hours long, to the North Pole, where in the summertime there's 24 hours of light, and in the wintertime there's 24 hours of darkness. Huge seasonal changes. No seasonal changes. We live in the mid-latitudes where there's about 6 hours difference in day length between summer and winter. But let's go back. So the first one between the Tropic of Cancer and the Tropic of Capricorn from 23.5 degrees north to 23.5 degrees south, that is the equatorial or tropical region. The tropics represent the location. This is the only part of Earth that gets direct sunlight during the course of a year. So in the subtropics, they never get sun hitting the ground at a 90-degree angle. Only between the Tropic of Cancer and Capricorn do you get the sun hitting the ground at a 90-degree angle. Just on the other side of the tropics are the subtropics from 23.5 to 35 north, from 23.5 to 35 south. Those are the subtropics. This is where the world's deserts are. The Atacama, the driest desert in the world, the Kalahari, and the Skeleton Coast of Namibia, most of Australia, the American Southwest, the Sahara, Saudi Arabia. All of those are in the subtropics. We live in the mid-latitudes, 35 to 55 degrees north, 35 to 55 south. In fact, if you look at how much land there is in the mid-latitudes in the northern hemisphere compared to the southern hemisphere, that's going to be really important later on. That, again, the farther away from the equator you go, the bigger the difference in seasons between summer and winter. So at the equator, no difference. Arctic, huge difference. So the mid-latitudes where we live, most people on the planet live in the mid-latitudes. 35 to 55. From 55 to 66.5 is the subarctic, and the Arctic is above the Arctic Circle. The Arctic Circle is at 66.5 degrees north. The Antarctic Circle, 66.5 degrees south. Vocabulary words. The word Arctic refers to bears, Arctos, bears. So the Arctic Circle is the circle with bears. The Antarctic Circle literally then is the circle without bears. Easy to remember, because they've got penguins. All those delicious, delicious penguins wouldn't exist if we had polar bears in Antarctica. So those are the 5 zones. You're going to need to know the latitudes of the equatorial, subtropical, mid-latitude, subarctic, and Arctic latitudinal zones. Latitude is just the angle between a location and the equator. For example, this dot is 49 degrees away from the equator, and if you connected all the dots that are 49 degrees away from the equator, you'd end up drawing the 49th parallel. The lines of latitude are called parallels because they're parallel. The equator is the longest line of longitude, the longest parallel, and then the rest of them keep getting shorter and shorter and shorter till at 60 degrees north, it's about half their circumference of the equator, about 40,075 kilometers, about 20,000 kilometers if you're to walk around the 60th degree, the 60th parallel. And when you're giving latitude, you don't need to say the word latitude. So this would just be 90 degrees north, 49 degrees north. If you're saying 49 degrees north, you don't need to say north latitude. North can't be anything but latitude. So be like the cool kids and just say 49 degrees north. The 90th parallel is just a dot, because a 90-degree angle to the equator would be a dot. So the 90th parallel is, in fact, it has no length. Lines of latitude, again, angular distance north or south of the equator. Latitude plays a huge role. Above this line right here is the Arctic Circle. Above the Arctic Circle, you have 24 hours of daylight. In the summertime, we have 14, 15 hours of daylight. And then in the wintertime, we have the opposite. We have like a 9-hour day. We have a 9-hour day in the wintertime, and we have a 15-hour day in the summertime. So above this line in the wintertime, there are 0 hours of daylight. Nothing. You get nothing. So, in fact, looking at Mexico, they've got over 10 hours in the winter and under 14 in the summer. So if we went to the equator, you'd see that there's no difference between summer and winter. 24 hours difference between summer and winter. That's also going to affect, then, how much energy comes in from the sun. So the tropics are going to be warm. Part of that is going to be because they get more energy from the sun. In fact, all of it is because they get more energy from the sun. You can see elevation playing a role. The other 5%. Latitude is going to explain 95% of everything. The other 5% is going to be plate tectonics. So plate tectonics made these mountains. These places are high. Because they're high, there's fewer molecules to filter out ultraviolet light. So the highest UV values are going to be on the equator at high altitude. Ultraviolet light is important. It's necessary for human health. Our skin makes vitamin D from ultraviolet light. So if you're in the tropics, you're going to be making lots of vitamin D. In fact, if you're in the tropics, the problem is too much energy from the sun. Ultraviolet light is so powerful that it breaks the bonds that hold our DNA together. That when your skin is tanning, it's because your body is producing more melanin because your body realizes that it's been damaged by ultraviolet light. So low values of ultraviolet light. In fact, the USDA in 1936 or so said that if you're African American and you live north of 36 degrees, you need to take supplemental vitamin D. This isn't an issue anymore because everybody gets enough vitamin D in their food now that we manufacture it and put it in food as a supplement. But prior to that, for example, in the Soviet Union, they would actually bus children south to get sunshine in winter so that they wouldn't get diseases from not having enough vitamin D. So if you're in the tropics, the issue is getting too much sunlight. So your body's going to produce more melanin to protect you from skin cancer. If you're at a higher latitude and you have too much melanin, it'll block too much ultraviolet light, and you won't be able to make enough vitamin D. So one of the functions of this is skin color. So all skin color tells us is where your genes have been for a long period of time. If your genes have been hanging around close to the equator, you're going to have darker skin tone to protect from ultraviolet light. If your genes have been hanging out closer to the poles, then you're going to have less melanin because you're not going to be receiving as much ultraviolet light. And in fact, if you had this much melanin, you wouldn't be able to synthesize enough vitamin D. On the other hand, if you took people from this region without lots of melanin and brought them as convicts to this country, you'd expect to find really high rates of skin cancer. So if you're looking for a career that is future-proof, I would recommend going into dermatology and then moving to Australia to treat all of the pale white people that are now in the tropical sun. Longitude. We've talked about latitude. Latitude is north and south. Longitude is east and west. So the lines of longitude are called meridians. They're all the same length. The lines of latitude, the meridians are all the same length. Again, it's an angular distance, in this case, east of the equator or west of the equator. It goes from 0 degrees to 90 degrees west and then 180. You don't need to say east or west with 180, just like with the equator, you don't need to say north or south. It's neither. So 30 degrees, 60 degrees east, 90 degrees east, 120 east, 150 east, 180 on the other side. Latitude, or rather longitude. So let me back up. Latitude is how far north or south of the equator you are. If you can see the North Star at night, the angle of the North Star against the ground is your latitude. So humans have been able to figure out their latitude for thousands of years. The Vikings were able to sail from Europe to North America. All they knew was their latitude. They had no idea how far east or west they were, but they knew how close to the equator they were just by looking at the angle of the sun or the North Star over the horizon. How far east or west you are is your longitude. And if you're in the middle of the ocean and there's nothing to see except water, you've got no idea what your longitude is, which is a huge problem. So, longitude is how far east or west you are. In the 1800s, the British held a contest to figure out a way of finding your longitude if you were at sea, and it turns out you need a clock. It works like this. Earth rotates through 15 degrees in 1 hour. So we have 24 time zones because there's 24 hours in a day. So each of those time zones is 15 degrees wide. So to figure out your longitude, you could have 2 clocks. This is a clock. This clock fit inside a box, 4 feet by 4 feet by 4 feet. And to figure out your longitude on board a moving ship, you need 2 of these suckers. So it works like this. 1 clock you keep on your home port time. And the other clock, every day when the sun is as high as it's going to be at noon, you adjust that one and reset it to noon. So let's pretend that we leave England. We're sailing along for a week. We look at the home port clock. The home port clock says it's 1 o'clock in the afternoon. We look at our local time. It's 1 o'clock. There's 1 hour difference. We're 15 degrees away from Greenwich. So it's a really simple method of finding your longitude because all you have to do is look at the difference in time between Greenwich and where you are. But the problem was being able to make a clock that would be accurate enough because the home port clock you never set. You just wind that clock every day. You don't adjust it for running fast or running slow. You're just hoping it's running accurately. Galileo had previously suggested this, but it wasn't until the 1800s that John Harrison was able to build a clock that would be accurate enough to tell your longitude on board a moving ship that's been at sea for months and months and months. Because previous clocks have been grandfather clocks with a pendulum. Pendulum isn't going to work if you're on a moving ship at sea. This was the H4. He went through several different versions. This is the H1. The H2 looked about exactly the same, except it fit inside a 3 foot by 3 foot by 3 foot cube. This one would fit inside a big coffee can. This was the H4. This was the standard issue aboard British naval vessels. And this is a stick chart. Up until relatively recently, the best navigators on the planet were Polynesians, who were able to colonize and populate all of Polynesia, sailing out from Indonesia as far across the Pacific to Easter Island, to the Galapagos. No, that's not true. So the best navigators in the world were Polynesians. They were able to populate the entire Pacific, coming out of Indonesia all the way up to Hawaii, all the way out to Easter Island, or Rapa Nui as the Polynesians call it. And this is a training aid. This isn't a map that they would carry on board a ship. Each of the shells represents an island, and the sticks represent the pattern of waves at different times of the year. And then as the waves hit the islands, they change direction. And by looking at the patterns that the intersecting waves make as they go through the islands, a Polynesian navigator would be able to tell where they are. So as the waves come in and hit an island, the waves bend, they slow down and change direction as they approach the land. Here's Santa Barbara. You can see you've got the lines are pretty much parallel coming in here. As they get in close to shore, they slow down, and so they start to wrap and change direction. And the same thing happens when waves hit islands out in the middle of the ocean. The waves change direction, so you'd be able to tell where you are. Latitude and longitude. So when you're giving latitude and longitude, that's the way we identify locations most of the time. We're going to give the latitude first, so how far north or south. And then the longitude, how far east or west of the prime meridian. So this location looks like it's 48 degrees north, 60 degrees east. So here's 48 degrees north. This would be the 48th parallel. It's 48 degrees north of the equator. And this dot is 60 degrees east of the prime meridian. So here's the prime meridian, and this dot appears to be about 60 degrees east of the prime meridian. So time zones. I mentioned them before. There's 24 time zones. Each time zone should be 15 degrees wide. They're not exactly 15 degrees, so that we don't have to chop up states and have one time zone on Pacific and one part of the state on Mountain Time. They also zigzag. This is the date line. The date line zigzags to go around countries. Otherwise, like you can see, it would have chopped this part of Russia. So here it would be Monday and here it would be Tuesday. The international date line is magic. When you cross it going west, you add a day. When you cross it going east, you lose a day. So you could take off from Hawaii on Monday and land in Wellington Tuesday. Or even weirder, you could take off in an airplane from Wellington on Tuesday and land in Honolulu Monday. So you'd get to redo Tuesday all over again. That's just weird. Weird. The international date line, again, it zigzags to avoid countries. It zigzags and goes all the way out here because the island nation of Kiribati, they didn't want to cut it in half again. So half of Kiribati would be on Sunday and half would be on Monday. They're all on Monday time. Daylight savings time, I'm not going to talk about it. I hate it. I've never understood it. You don't save any time. And that's where I'm going to stop for the second video. The third video will be on maps, cartography, and tools geographers use.